Welcome back. Here we have this structure. You can see that you have this parabolically shaped curve on which you have a sphere, and then a cable goes from the sphere over a pulley, and then you have a box on the other side. This parabolically shaped hill from this point here up until this point here, it follows this parabolic function. Then this sphere itself, its mass is 4 kilograms. The center of the sphere is located at x equals 0.4 meters and y equals 0.4 meters. This cable here is at 60 degrees, and this structure is at rest, meaning that the sphere nor the box accelerate anywhere. And obviously we neglect the mass of the cable because it's too small compared to the masses of the sphere and the box. And so what we need to do, we need to find the mass of the box, and we also need to find a normal force that the surface exerts on the sphere. Now, before I let you do this problem, a couple of words about pulleys. First of all, we assume that the pulley is frictionless. What it means is that when the pulley rotates, for example like this, it can rotate freely. There is no internal friction in the mechanisms that would work against this rotation. Of course, in reality there is always some friction, but in good quality pulleys, it's very small. So in this course we can neglect it. However, if you perform more advanced analysis in engineering, then it should be taken into account. But here, assuming it to be negligible, it's a good enough assumption. On the other hand, we assume that there is good enough friction between the wire and the pulley, so that the wire would not start slipping on the pulley. Finally, we assume that the pulley has negligible size. Why is that important? Well, in physics, we have something called mass moment of inertia, or big I. Essentially, it's resistance to rotation. The bigger the mass moment of inertia that an object has, the harder it is to rotate it. If I have two pulleys here, and both of them have the same mass, but pulley B has a bigger radius than pulley A, then that makes the mass moment of inertia of pulley B greater than the mass moment of inertia of pulley A. So it's harder to rotationally accelerate pulley B. You need more moment for that. Because remember, in one of the videos I mentioned that moment equals the mass moment of inertia of an object times the angular acceleration of that object. And so, if you have a bigger mass moment of inertia, then in order to accelerate an object angularly a certain amount, you need more moment for that. But if we assume negligible size for the pulley, then essentially I'm saying that the mass moment of inertia of that pulley is very small. So small that we can neglect it. And that's a reasonable assumption when the other objects in the system, like the sphere and the box, when they are considerably bigger than the pulley. And so this assumption allows the pulley to freely rotate, allowing you to focus only on the sphere and the box. And now, try solving this problem by yourself. Try to calculate mass B and the normal force, and you'll see the solutions in the next video. Thank you very much. Welcome back. So let's now determine this normal force and this mass B. Let's disassemble this system a little bit. So this sphere rests on this hill in this location, and it touches the surface right here. And so we can have a tangent straight line here, like this. And this normal force is perpendicular to this straight line, which is tangent to the curve. So I'm going to draw this line here. This is the sphere. This is the normal force, which is perpendicular to this tangent line. And here's the cable, which is this one here. And note that you cannot assume that this cable is parallel to this red line. There is no reason to assume that. Even if they look parallel right now, you don't know that for sure. And so what I will do, in my mind, I will mentally cut this cable. And so this cable continues from here. This is your pulley. Then again, I will mentally cut the cable here. So it's right here. And this is the box. The box has some kind of force of gravity, and it's the mass of the box times g. Then also the sphere has some kind of gravity, and it's 4g, because the mass of the sphere is 4 kilograms. The force of gravity points down. And so since in reality your structure is not accelerating anywhere, your sphere is not going up nor down, you have to have a force here, let's call it F, which holds the sphere in place. And since this is a cable, you have the same force here, F, because that's how it is with cables. The internal force gets transmitted along the cable, so whether you cut it here or here, internally the cable still experiences the same force. Now that's of course only if you have this configuration with one pulley. You can have different results when you have several pulleys and you combine them in a smart way, but we will look at that when we look at frames and machines. But here, this F is equal to this F. You have one force that comes from here, and then another force which is equal in magnitude and opposite in direction that comes from this side. And the same thing here. That's Newton's third law. Now we know that this is 60 degrees, but it would also be nice to know this angle here, let's call it theta. And so what we can do, we can take this function y equals 2.5 times x squared, and we can take its derivative, dy over dx, and that will give you 2 times 2.5x, in other words, 5 times x. Now remember what the derivative gives you. It gives you the change of y with respect to x. It gives you the slope of this red line. So essentially, I can construct a right triangle here, and I have delta y here, delta x here, and so the slope of this red line here would be delta y over delta x. That's the slope of the line that is tangent to this parabolic curve at x equals 0.4 meters. And so in order to find that slope, I have to replace this x with 0.4. So dy over dx at x equals 0.4 meters, that's 5 times 0.4, and that gives you 2. So delta y over delta x equals 2. But that also equals tangent theta, because that's what tangent theta is. It's delta y over delta x. And so that means that theta equals inverse tangent to 63.4 degrees. And now that we have this angle, we can construct a free body diagram for this sphere. So this is the sphere. And now, of course, in reality, the force of gravity is in this direction. This is your 4g. But what I would like to do, I would like to decompose it perpendicular and parallel to the surface on which that sphere rests. So let me call this one FG perpendicular, because it's perpendicular to this line. And this one, let it be FG parallel, because it's parallel to this line. And so this angle here, it's also your theta. It's also 63.4 degrees. You can think of it like this. If instead of 63.4 degrees, you have 0 degrees here, then your theta here is also 0 degrees. But once this angle is 63.4 degrees, then also your theta is 63.4 degrees. And if this becomes 90 degrees, well, then you have this situation where this is 90 degrees, and also this here, it's also 90 degrees. And then you also have 90 degrees here. Therefore, in our case, theta equals 63.4 degrees. And so I can say that FG perpendicular equals, and so if this is 4G, then you have 4G times cosine and then 63.4 degrees, and FG parallel equals 4G times and then sine 63.4 degrees. Now the thing is that I don't really need these two components. I just wanted to show you that you can decompose them like this. However, what I do need, I need this angle between the normal force and this horizontal line. So let's call it alpha. Now the thing is that this normal force is equal in magnitude and opposite in direction to this FG perpendicular. And you know that because the sphere is not accelerating nor in this direction nor in that direction. Which means that if I define this side to be positive and this side to be negative, then I could write that the sum of the forces along this line, they must equal 0. So the normal force minus FG perpendicular, they must be 0. That's why your sphere is not accelerating along this line. So N equals an FG perpendicular. So you know that they have the same line of action, which means that this alpha here is also this alpha here. So right away you can calculate your alpha because you see that you have 90 degrees here. So you can say that alpha equals 90 degrees minus theta. So you just subtract this theta from 90 degrees and you get your alpha. And that will give you 26.6 degrees. That's your alpha. And now we can construct our traditional free body diagram. This is your normal force here. Then this thing here is 26.6 degrees. And now we have one more force here. We have this F, which points in this direction. And you already know that it's 60 degrees. So essentially these three forces, 4G, N, and F, they are applied to this point here that we can consider as a particle. And so this point here is called A. And now what is this force F? Well, if you look at this side of the structure, then you can clearly see that if I create this boundary here, and I have a force here, mb times g, and this green box is not accelerating nor up nor down, then from the equilibrium principle you see that you have F minus mb times g, and it equals 0, and that means that your F equals mb times g. And since this F is the same like this F, this one also equals mb times g, which means that this one equals mb times g. And so now that we have our free body diagram, and let me also say that this is positive x, this is positive y, now we can apply our equilibrium principle. So the sum of the forces in the x direction must be 0. That's minus n times cosine 26.6 degrees plus mbg times cosine 60 degrees, and that equals 0. And this mbg, that's your F force. And then the sum of the forces in the y direction must also equal 0. So you have n times sine 26.6 degrees plus mb times g times sine 60 degrees minus 4g equals 0. From the first equation, you can write n equals and then this expression. You simply do the algebraic manipulation and you express n in terms of other variables. Then in the second equation, you replace this n with this expression here. And if you do that, then your second equation will look like this. Here I've simply replaced n with this expression. Then from here, you know that you can have tangent 26.6 degrees, and now you only have one unknown, mb. And so now, you simply factor out mb times g, and then on the other side, you put 4g. So this term I simply put onto the other side of the equation sign. Then I can cancel out the g's, and so in order to write less, I'm just going to say that this entire thing that you can calculate, it's c, and so mb equals 4 over c, and that gives you 3.58 kilograms. So that's the mass of this box. And now you can take this formula here, and you will have n equals, your mb is now 3.58 kilograms times g times cosine 60 degrees over cosine 26.6 degrees. And if you calculate that, then you will have 19.7 newtons. So that's your normal force. Your mb equals 3.58 kilograms and your normal force equals 19.7 newtons. Thank you very much. Welcome back. So I have another spring exercise here. You can see that you have a box here that is hanging from the hook. You have 3 meters from this location up until this location. You also have 3 meters here, 4 meters here. The system is in equilibrium, meaning that this box is not accelerating anywhere. But now, the springs here are different. So this spring, KAC, it's 20 newtons over meter. Then this one here, KAB, that's 30 newtons over meter. And then KAD, that's 40 newtons over meter. And another piece of information that I will give you is that this spring here, the one that goes from A till B, when it's unloaded, then its initial length, or L0, it equals 3 meters. So that's only for this spring here that goes from A to B. And that's when it's not loaded. So these are your initial conditions, and now your job is to compute the mass of this box. So try it out by yourself, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now find the mass of this box. First of all, because of the fact that we know the length of the unloaded spring that goes from A to B, we can right away calculate the force in the spring. So if I draw my free body diagram here, this is positive x and positive y, and the free body diagram will be drawn for this point here, point A. And so first of all, we know that it has a force of gravity, which is md times g. That's because you have a force of gravity here, md times g. And so if I put a boundary here, then since this entire thing is not accelerating anywhere, and I only have one spring here, then this force here also needs to be md times g, which means that this point A has the same force but in the opposite direction. And that's why I know that I have md times g here. And now I have two more forces. I have a force here. Let me call it FAC. And since you have 3 meters here and 3 meters here, you right away know that this is 45 degrees. Then you have another force, FAB, and let's call this angle theta, but it's easy to calculate because you have 3 meters here and you have 4 meters here. So essentially, you have this right triangle here. This is 3, this is 4, and that means that tangent theta equals 3 over 4. So theta equals inverse tangent of 3 over 4, and it's 36.9 degrees. That's your answer for this angle. So I'll just put here right away 36.9 degrees. And now we have 3 unknowns. We have this one, and this one. But from the equilibrium principles, we can only have 2 equations. Therefore, this extra piece of information that I gave you, which is this one here, when this spring from A to B, when it's not loaded, it's 3 meters. From that information, you can obtain your FAB. So your L0 AB equals 3 meters. But right now, because of this box, this spring is loaded. So what's the distance from A to B right now? Well, LAB equals square root of 4 squared plus 3 squared. That's square root of 25, and that's 5 meters. From that, you can calculate your elongated part for that spring, which is this one. That's 5 minus 3 equals 2 meters. And so FAB equals the spring constant times SAB. So that will be 30 times 2, which is 60 newtons. So there you go. You know that this force is 60 newtons. And now you just apply the equilibrium principle here on this free body diagram. The same thing, the sum of the forces in the x direction must equal 0. So it's this one. And then in the y direction, it's this one here. From this first equation, you can very easily obtain FAC. After some algebra, you will find that this force equals 48 times square root of 2 newtons. I will keep it in this form in order to preserve precision. Otherwise, I'm going to have lots of decimals there, and I will lose some of the precision. And then I take the second equation. Since I know my FAC, I can simply take it and put it here. And so MD times G, which is here, I'm just going to put it to the other side, and it equals this one. And then what I can do, I can divide all this by G. So this G will go away from here. And that will give me 8.56 kilograms. So the mass of this box equals 8.56 kilograms. Thank you very much.